we want to start giving names to some of the features that we might see on a graph. For instance, let's look at this point right here, where the function takes this little dip. Now, it's not the absolute lowest point on the graph, because the function gets smaller over here. But if we just look near this point, say in this little region, then this point is the lowest. So what we would say then is that our function f has a local minimum at this point. The word local reminds us that we don't have to go very far. Just as long as the point is the minimum value of f in this tiny neighborhood, then it's a local minimum. Similarly over here, this point is also a local minimum, since it's the lowest in this small part. Now, this point might also be where f takes its overall or global minimum, or it might not if f does something like this over here. But it's definitely at least a local minimum. Formally, we say that f has a local minimum at a point x equals a if f of a is less than or equal to f of x for any other x that is near a. And what we mean by near a is just within some small distance from a. And we have a corresponding definition for local maximum. You just reverse the inequality. For instance, there's a local max right here. It's not the global max, since over to the left f gets a little bit larger, but that's fine. If we just look at points that are near this point, say from here to here, then this point is the maximum. So we've got a local max at this point. Okay, so we've defined local minimum and local maximum. Just a quick grammar note. The plural of minimum is minima. It's Latin. So here we have two local minima. The plural of maximum is maxima. And if you want to refer to local minima and maxima together, you can call them local extrema. And extrema is the plural of extremum. How do we go about finding local extrema? Well, we can use the derivative. Let me erase some of this and note that if we have a point where the tangent line to the graph has a positive slope, then f is going to be bigger to the right of the point and smaller to the left of the point. So the point can't be a local extremum of either kind. Similarly, if the tangent line has a negative slope, then f will be smaller to the right and bigger to the left. So what does that leave? Well, we could have a point where the tangent line is horizontal, that is, f prime of a equals 0, something like this or this, perhaps. Or, there's another possibility. We could have a point where there is no tangent line. That is, f is not differentiable at a. And that could be a corner point like so. And that's a local maximum, what I just drew. We're going to give these a name. We say that if f prime of a equals 0, or f is not differentiable at a, then a is a critical point of f. And what we just proved is that every local extremum must be a critical point. You might be wondering, why bother with two different terms, local extremum, critical point? The reason is the following. Every local extremum must be a critical point, but not every critical point is a local extremum. To give an example, if the graph is like this, then the tangent line here is horizontal, f prime equals 0, so that's a critical point, but it's not a local min or a max. So we're going to need to develop analytical methods for determining whether a critical point is a local max or a local min or neither. But first, we want you to get some practice using these terms. So see you in a little bit.